Well, welcome to this new series. As you've probably gathered from the brochure, if you've read it, or the online description, I'm going to run through in these lectures quite a number of different sports. And I'm going to have some focus upon the upcoming Olympics. We've started the series a little later than I usually start, so that we can end a little later in 2012 and be a little closer to the Olympic Games themselves. I picked on one particular topic here, a rather fashionable one with Mr. Bolt. At least has the advantage that everyone here will have heard of him. Although I think when I first looked up some pictures, I discovered that there is a rather successful and in some circles well-known racehorse who's called Usain Colt. And you will tend to come upon him quite often in your Google search. Well, I'm just going to focus on Bolt's 100-metre running today. I mean, there's a lot to be said about 200-metre running, but there isn't time to talk about that as well today. Here's a picture I prepared which shows the evolution of the men's 100-metre sprint record back from about the time of the 1908 and 1896 Olympic Games, sort of times when I could have won it, and moving forwards, the change in the size of these bars reflects the accuracy to which timing took place. So from about here onwards, you can see fully electronic timing results in very small error bars. You're suddenly timing to 100th of a second rather than just to a 10th. And what you can see here from this sort of period in the 1930s, 1936, Harold Abrahams would have been running about 10.6 seconds for 100 metres, and you're down in Bolt territory just below 9.6. Although there was a long period when there wasn't really very much change, when the record sort of hung around 10 seconds and then around 9.9. But really the progression of this record is really quite slow. If you compare with what happens in other sports, and the most interesting case is to compare, say, swimming with running. Now, if we pick not an event that goes over the same distance, but compare events that are for about the same time, then we would be comparing 100-metre swimming with 400-metre running. So the men's 100-metre swim back in 1968, it would have been Mike Weddell, who wins the Olympic Games in Mexico City in 52.2 seconds. It'd be hard pushed to qualify for the women's final now with that time. It wouldn't even make the American Olympic team. Nowadays, 46.91 with a little bit of help from funny swimming suits, hydrophobic swimming suits, but even without them, you're 47 seconds. So since 1968, over this 43-year period, there's been this huge 6.5 second or so improvement in performance. Now look what happens in 400-metre running, 43.8 seconds to win in 1968. It's a very, very good record. A few years ago now, Michael Johnson, 43.18. There's almost nobody running even this today. So there's almost no progress, maybe about 0.6 of a second in running for the same period of time. We'll see in later lectures some of the reasons why what's happened in swimming has happened. I mean, in short, swimming is the most technical, probably, of all swimming events, where research and understanding of hydrodynamics and motion and resistance and technique produces enormous improvements in performance. Running, it's not so easy. The basic motion is much simpler. You're moving through air rather than through a liquid. So here you see the progress of the men's records, and here's the progress of the women's world records. It's really pretty relentless, and it shows no sign of stopping. Every time there's a major championship in swimming, there's a world record in almost every event. There are no long-standing records in the shorter events. If we look at a whole span of events, there's a rather interesting systematic relationship which extends even beyond the schedule of events that you would see in the Olympic Games. So if you take any running event and you work out the average speed of the best performer, so this is just dividing the distance by the time, so it will be 100 metres divided by 9.58, and you do that for every event all the way up to the marathon, say, then what you have is the average speed at which the athlete is performing that distance. And if you plot that against the distance in metres, it's a very, very good straight line on a log-log plot. And what that means is that the average speed falls off like a power of the distance, and that power is minus 0.11 to very good accuracy. And it's pretty much exactly the same for the women. So the two lines are parallel. So there's this very good systematic relationship between human running performance and distance. And you can keep this going to ultra-marathon distances and beyond. You can do it for other sports. You'll get a different curve, but pretty much you'll get a straight log-log relationship. Something I'd noticed that sports scientists have never seemed to take much interest in are the Paralympic performances, and particularly wheelchair events. One of the unique things about the 2012 Games is that they are the first ones where the Paralympics and the ordinary Olympics are not separate events. They are regarded as one and the same. They're part of a single Olympics. And sports scientists have really spent very little time studying what goes on in Paralympic events, with the exception of the arguments about Mr. Pistorius. Here's the same plot for wheelchair events. So you work out the average speed against distance. And if you do that, you soon recognize there's something very, very strange about wheelchair events. And that is, there's essentially no fall-off in the average speed against distance. This is something you might suspect if you just look at the famous names in this sport. You find people like David Weir, for example. They have gold medals in the 100 metres and the 800 metres, and they're winning the London Marathon. This is inconceivable in regular athletics events. So there's an enormous range of competitions in which the top athletes in wheelchairs take part. And this picture really tells you why that happens. In fact, the average speed in the 10,000 metre world record is lower than the average speed in the marathon world record. So no doubt going around lots of bends on the track is something that's rather awkward, whereas the marathon, there's more marathons to compete in, it's more competitive, but it's a better terrain for wheelchair athletics. There's also a strange lack of standardization in wheelchair weights. Lots of standardization in where the center of gravity must be and the height, and things mustn't hang off the sides, but none about their weight, which is most peculiar because on the track rolling friction is a key form of resistance. So if you look at those formulae again, you see really these curves are almost flat. There's virtually no dependence, no significant fall-off in average speed with distance. Well, let's get back to Mr. Bolt. What we're interested in is looking more carefully at his past performances and what he might do in the future, how he might run faster without actually having any improvement whatsoever physiologically in his running performance. How could that be? Well, at the Beijing Olympic Games, he ran a time of 9.68 for 100 metres, and in 2010 at the World Championships, he improved this by a whole tenth of a second to 9.58. You'll see here it says 9.69. It's a sort of instant time on the electronic clock. Gets rounded down to 9.68 eventually. So these are the performances. First of all, when you look at a performance like that, you look at these times in athletics events, you have to divide them into two pieces. They're composed of what you might call a run time, the time it actually takes you to run 100 metres, and a reaction time, the time that it takes you to respond to the gun. And I was alarmed to see recently, New Scientist had an article some months ago by a whole group of Stanford biologists analysing what would be the fastest speed that Bolt could run, who, having missed this point, then ended up making future predictions about what Bolt's ultimate speed of running would be that were actually slower than the speed at which he runs at the moment, which is rather unfortunate. Now, when you look at high-level athletics, what you have to realise is that the false start rule is that if you respond in any way, any measurable way, to the electronic triggering of the gun, in less than 1/10 of a second, or 100 milliseconds, then you are defined to have false started, whether you've left the blocks or not. So if you just exert some toe pressure on your starting block, that will register as a false start movement. And nowadays you don't have any grace, you don't have a second chance, as Bolt himself discovered, you will be disqualified for making that false start unless it can be shown that you were responding maybe to somebody screaming in the crowd or clicking their camera, in which case it will be a faulty start. So in Daegu last summer, attracted all the publicity, Bolt didn't even try to react quicker than 0.10. He reacted 0.104 before the gun was triggered. So this was a sort of failure of concentration. Well, these electronic triggerings of starts are important. When you and I were at school, maybe people started races by having a gentleman in an orange blazer hold a gun in the air and fire it. Well, nowadays he would be arrested by anti-terrorist police just before he fired the gun, so starters are not allowed to own pistols anymore, let alone fire them. But as you probably realise, that if we have our runners here along the start line, and here's our starter with his gun, say 5 metres away on the infield, then the person in the outside lane is probably about 15 metres away from the starter, and you have to worry about the speed of sound. Okay, speed of sound is about 340 metres per second, and so the inside lane here is going to hear that sound of the gun rather sooner than the person on the outside. And the benefit that being close to the starter gives is obviously 15 minus 5 divided by the speed of sound. It's about 0.029, 0.03 of a second. And that's easily enough to be the difference between winning and coming fourth. So you cannot start high-level international sprint races by firing guns from a particular point on the infield. So what you do is that you have microphones, in effect, and there is an instantaneous transmission of the sound of the gun to each starting point at the same moment. If you lived in America long ago, you might have had the experience of seeing a 200-metre race run on a straight track. There used to be one of these at Oxford when I was a graduate student there at Iffley Road. It was changed in 1975. But in the USA, it was quite common to have 200-metre straightway tracks, as they were called. And there were always surprisingly fast times recorded on 200-metre straightways. Of course, you had the possibility you had wind assistance behind you all the time. But the other reason was that timekeeping really was a very dodgy business. So the timekeepers are at the finish 200 metres away from where the starter fires his gun. So there is a sound travel time of 1.7 seconds between the start and the timekeepers at the finish. So there was huge latitude for uncertainty and error as a result of that. So before you have electronic timings, this is a very awkward event to try and run. Well, what used to happen in those days before electronic timing and before people started defining, therefore electronically, what a false start was was that you would have athletes who were, I would call them professional anticipators. So the most famous anticipator, was the 1960 Olympic champion Armin Hari from Germany. So he perfected the art of starting on the sound of the gun. So he didn't wait to hear it. He would simply, I suspect, listen to the starter, starting many earlier events in the program. And he would eventually work out what was the delay that was being used by the starter. Most starters have a little system. They sort of say, get set, 1001, bang. So he'll do that every time. So if you listen carefully to the starter, you can work out what his little delay is and make sure that you all say 1001 and off you go. So Hari perfected this. He equaled the world record at the time, 10 seconds flat. When he was subjected to some electronic investigation, it was found that he was reacting on occasions apparently with reaction times of 0.04 of a second. It's physiologically impossible, as we'll see in a moment, by a large margin. Here are some statistics here of reaction times of sprinters in major championships over a 6-year period. Here's their final time, and here's their reaction time. And remember, if you're below 0.10, okay, down here, you would be disqualified. So there are some outliers here of people who are really very, very fast reactors. You don't know if they're doing that systematically or it was just rather lucky. But you see there is a rather weak trend here that fast reactors get fast final times overall. But there is a trend nonetheless. And you can see where the sort of mid-range lies. Well, let's look at Mr. Bolt. The interesting thing about Mr. Bolt, he's one of the slowest reactors of all top athletes. Has the slowest reaction time amongst major sprinters. So here's an example from the Berlin World Championships in 2010, where he set a record of 9.58. And here is the split of each athlete's reaction time and then their running time. And you see Bolt is up in this 1.46 reaction time. Here are his rivals. You see they're all significantly faster, except for this gentleman here, and Patton at the end. I've highlighted these two, here's Dwayne Chambers and Burns. There's the case where you see Burns actually runs faster, significantly faster than Chambers, but because he reacts so slowly, he ends up finishing behind Chambers, although they have the same time. So back in the Olympic final, 2 years before, Bolt's even worse. He reacts in 0.165 of a second. Okay, so he's, I think, the second slowest reactor in that final. So this is not a one-off. Every time, he's a very slow reactor to the gun. If we look at physiological evidence of testing laboratory and testing of athletes involved in big championships, there's another curious feature of sprinters' reactions. So these are all the athletes that took part in sprint events at the Beijing Olympics. So here are men, here are women, here is the reaction time in milliseconds. So this is 0.2 of a second, 0.15, 0.1. And here are the histograms, and you can see where the means look like. It's about 0.168 of a second for the men, 0.191 for the women. Now this difference between men and women is not new to this data. It's always been something of a mystery ever since such data has been collected 70 or more years ago. There's always been this systematic difference between the average reaction time of men and women. Long ago, there used to be theories put forward to try and explain this, that it was, not so many women drove cars as men did. This doesn't apply now, of course, but there's no very good explanation, no clear explanation as to why there is this difference. It might just be directly linked to muscular power and strength, driving a response. But if you look at the statistics, you look at the number of false starts that there were in Beijing, so this is the number of people reacting to the gun faster than that 0.10 here, there were 25 by men and 4 by females. So this is consistent with this type of difference. You see, if females have a slower reaction time, they're much less likely to false start than men. And what this evidence implies is that there should be a different false start rule for men as there is for women. By a few milliseconds. Okay? You heard it first here. Here's another picture of these reaction time data and the fraction of athletes who are reacting at a particular reaction time. So 5% only are reacting within 0.12 of a second. So someone like Colin Jackson, who was probably the best consistent starter of all in modern athletics, consistently around this time, every time, never false starts. So it's a real reaction response. But 50%, you see, up about 0.145. You remember where Bolt was? He was 0.146, and then the Olympics, he was 165. So he really is well down the statistical distribution. His performance in Daegu, I can't even fit on this slide, because, of course, he reacted before the gun, so he has a negative time up here. And here he is, celebrating. So my first improvement tip to Mr. Bolt is to improve your reaction time. Okay? So if you can even get it down to 0.12, which is, although it's uncommon, lots of top athletes can do that consistently, then you'll lop 0.03 off your record, it'll be down to 9.55. Go down to the margin to 0.10, and you're down to 0.53. Okay? So that's our first piece of advice. The second thing we're going to look at is wind assistance. It's a picture here of a track that looks rather like one which I ran around rather a lot when I was young. And this sign here is telling you 2 meters per second. This is the maximum following wind that's allowed for a performance to be valid for record purposes. You can win the Olympic Games with a 10 meter per second following wind, and you can even set an Olympic record, but you can't set a world record. Well, wind assistance and wind resistance, which is more noticeable if you're running into the wind, what are the ingredients that affect it? Well, one that's familiar that you see particularly in cycling or if you watch speed skating, people attempt to streamline their body profile to reduce the area that they are presenting to the wind in the direction in which they're moving. So here's some pictures of a skydiver or extreme situation where if you're coming down head first like this, then the body area that you're presenting in the direction of motion is really rather small. If you come down at an angle like this, you're presenting something bigger. If you're laid out with your arms outstretched, you're presenting almost your whole body area. You're curved up. If you move those legs out, you'll present probably the maximum surface area and experience the most resistance. If you curve a bit, it'll be reduced. So you can see how manipulating your body shape allows you to change the speed with which you would fall if you're a skydiver. I'm not a skydiver, and Barrow's first law is, if at first you don't succeed, then skydiving isn't the sport for you. Well, let's look at what the role of the air is when you sprint through it. So suppose that you are sprinting along at some speed v, and you are presenting an area of your body in the direction in which you're moving, just like the areas on the previous picture. and we'll call this A for Mr. Bolt. Then what's the force that you feel as you move through that air? Well, if you run through air for a time t, what's the mass of this cylinder, this tube of air that you are sweeping out as you move? Well, it's the density times the volume. The density of air we'll call rho. What's the volume? Well, it's this area times the speed times the time. So this is the mass of air that you are displacing as you move for a time t at speed v through air of density rho. This thing I've called A dashed. It's the area you're presenting, but it'll have some other factor in there that'll determine where you're wearing some sort of Leica suit, so something that's more aerodynamic than wearing a duffel coat or a tracksuit or something like that. So there's a little fudge factor here, which will be of order 1, which will depend on details of how smooth your surface is. So the drag force from the still air, okay, it's opposing your motion, so I give it a minus sign, is going to be that mass times a measure of acceleration, Newton's second law. Acceleration roughly is the speed divided by the time. So here is the drag force if the air is still. Okay, it's the density, little fudge factor, the area times your speed squared. But what if there's a wind blowing? Okay, if there's a wind behind you, okay, it'll be advantageous. If you're going into a wind, you will have to do more work. You will need more force to overcome it. So if the wind is behind you and its speed is w, it'll be a positive wind. If it's a wind that you're blowing into, you're running into, a headwind, it will be negative. Okay? And so if you make this quantity w negative, this is positive, and you will need more force to overcome the wind. So when you see athletic performances, you'll see a sprint time, it'll have in brackets plus 1.0. Means there's a following wind of 1 meter per second. If it has minus 1.0, there's a headwind of minus a meter per second. So this formula we're going to do a number of things with. The first one is to think about people who run round whole laps, 400 meters, 800 meters, all the way up to 10,000 meters on the track, or even around the quad at Trinity College. And what we want to know is, is it a swing and roundabouts problem? Okay, if you would think that, well, you have the wind behind you in the home straight, you're going into it down the back straight, doesn't it just cancel out? Well, if you've been a runner, you know it's not like that. It's always harder running in the wind. So you never gain from running in the wind what you lose by running into it. Well, we can prove that with a little bit of mathematics. So here's the drag force on you if the wind speed is w and you're moving at v. It's proportional to the square of the difference. So what's the power that you need to overcome that? Well, power is force times velocity, so we just have to multiply this by another power of the speed. So it goes up to v minus w cubed. So this is pretty non-linear, okay, and that's the key to what happens, this cube. Let's idealize our track to be a square. Doesn't make any difference, but it saves us doing a sort of nasty integration. So imagine we've got a square lap, so we run along here, leg one, up here, along here, and down here. And for simplicity, let's imagine that the wind is going horizontally across here, where this big white arrow is. So this means that when you run across here, you will have the wind behind you, and the power you need will be just k, constant proportionality, times v minus w cubed. When you go up here, the wind is neutral. It's a crosswind. Doesn't affect you at all. So you just need kv cubed. When you run along here, you're going into the wind, and you need v plus w cubed of power to overcome it. When you come down here, the wind's neutral again. So what's the total power that you need for a lap? Well, you just add these four things together. Well, you've got 4 kV cubes, one from each one, and the minus signs here cancel out the term there, and you get 3 VW squareds from up here and another 3 VW squareds from here. And so the answer is 4 kV cubed plus 6 VW squared. So you see two things about this. First of all, it's W squared, so if I change the wind speed to the opposite direction, to minus W, the answer will be exactly the same. All you'll be doing is altering the direction of the arrows on the picture, running the other way round. Wouldn't make any difference. But you can also see that if there's no wind, the power you need is 4 kV cubed. So whenever there is a wind, the power needed is always bigger than 4 kV cubed. If you're worried about the wind being across here, if you make the wind go in any angle you like to the horizontal, you can do the calculation, you'll find that angle completely cancels out. You get exactly the same answer multiplied by cos squared of the angle plus sine squared of the angle, which is 1. So this is true for any wind direction. And it simply means that it's always slower running round laps in the wind than in still air. In the last year, there was an odd phenomenon of a wind-assisted marathon. So back in the spring, in April, at the Boston Marathon, this gentleman, Mr. Mutai, Geoffrey Mutai, not to be confused with another Mr. Mutai who won the London Marathon the following day, another Kenyan athlete, no relative. He took more than, I think, about 2.5 minutes off the world record in this performance in the Boston Marathon. So 2 hours, 3 minutes and 2 seconds. And the second runner, another sort of 10th string Kenyan athlete, probably is 4 seconds behind, also way, way ahead of the world record. Now this course is very strange. The Boston Marathon is not like the London Marathon and all other top marathons. It doesn't have many laps. It's a single point-to-point course. And it's not valid for record purposes because of that, because there's a rule that if you have a point-to-point course, then the finish must not be more than 42 meters lower than the start. You can guess why. There are strange marathons in America that people seek out where there's enormous variations between the start and the finish height, like 2 miles or something. So you can run your marathon about an hour. But the Boston course drops 139 meters from start to finish. It has some hills in between, so it's not quite as bad as it sounds. But what happened in this marathon was that it was really very windy, and it was clear that, in effect, the runners were running an entire marathon with a strong wind behind them. And one of the most interesting comments was when the winner was asked about this. He said, oh, he didn't think that was the case. I never felt there was any wind. Okay? I couldn't feel any wind, which I thought was an absolutely conclusive remark. Because remember what the drag force looks like that we just looked at, proportional to the density, proportional to the speed you're running minus the wind speed. So if the wind speed is the same as the speed that you're running at, you will not feel any drag force. Okay? And in fact, there were then independent reports from people around the course saying that they thought that there was a wind speed of around 5 meters per second or so, and it was quite blustery behind the runners. Well, if you look at the winner's average speed, this time, where's his time? 2 hours, 3 minutes over his marathon course, lo and behold, the average speed is 5.7 meters per second. So in fact, the following wind was very, very close to his average running speed. In effect, he might therefore have been feeling no resistance. The situation is a bit more subtle, but when you use the formula that we've looked at, what you estimate is that if he's just running on his own, no one around him, he's got a 3% power saving over this race, which means that really this fantastic time of 2 hours, 3 minutes is equivalent to 2 hours, 6 minutes and 45 seconds without that extra assistance. But we might be being harsh on him. We're assuming that he's always got the wind at his back blowing him along. If you look at pictures of the race and film, he's running in a group for the first half. And so people always think about athletes and cyclists shielding themselves from the wind by hiding behind people. But you don't want to be in front of people because that's stopping you feeling the benefit of a following wind. So he might not have had the full benefit of the wind in the first half. In the second half, where he breaks away from everyone else, he does have the full benefit. And if you look at the split time for the second half of the race, it's quite astonishing. 61 minutes and 4 seconds for the half marathon for the second half. It's quite amazing. Obviously wind assisted. So if we take that detail into account, he's really running 2 hours, 4 minutes and 52 seconds. Still extraordinary, but a little bit of analysis of what's going on shows you that wind is really very important. The current world record, by the way, has since been reduced on a lap course to 2 hours, 3:38. If we think about how do we allow for wind assistance in 100-metre sprinting, we can work out the power you need. Typical sprinter weighing about 70 kilograms. We want to know that density of air. That was the other factor. That area that you're presenting to the wind. So we know all these numbers. And when we put them in, again, about 3% of the runner's effort, power generated, is going into just overcoming the air which he's moving through. And so if we just do a little bit of algebra, we can then calculate, well, if there was a wind W, what would the time be that you would take to complete 100 metres compared with the time that you would take if there was no wind? And it's a rather simple formulae, okay? The O3 is the 3%. So this is the time you would record if there's no wind, and this is the wind speed, and this is the time that you would record if there's a wind W. Following wind is positive, okay? W positive. If you had, you're going into a wind, then this is minus, and this becomes plus. Now, many years ago, I remember writing a short article which derived this formula and then applied it to the top 10 100-metre runners of all time, changing all their performances to what they would have done with zero wind. And the result's rather interesting because the fastest runner in the world was not the world record holder. Okay, so because the world record holder had set his record with the wind just below the valid 2 metres per second, whereas there are other performances with essentially no wind that were just 100th or 200ths behind and far, far superior. Well, what about Mr. Bolt? What's the wind situation with him? And this is rather remarkable. Although he is a very slow reactor to the gun, he really gets, in practice, he's had almost no help from following winds in his record performances. So that last formula tells you as a useful rule of thumb, for each 1 metre per second of following wind, you get an improvement of about 0.1 of a second on the finishing time. So if you run 10 seconds flat with a 1 metre per second following wind, this is worth 10.1 seconds in still air. So when Bolt ran 9.68, the wind was actually zero. So there was no wind at all. If someone had opened the doors in the stadium behind him and let in a 2 metre per second following wind or turned on a big fan, jet engine behind him, what would have happened? His 9.68 would have turned into 9.48 without him having to generate, as it were, any more power. That's what I mean by improving without running any faster, without doing anything physiologically different. In Berlin, when he ran 9.58, there was a following wind, but it wasn't that dramatic. It was 0.9 metres per second. So in this case, if you had bumped that wind up to 2 metres per second, it produces a 9.47. So these two performances, although they look 0.1 of a second different, are intrinsically very similar, almost identical, when you allow for the two winds. But you can see how much better he can do just if he sort of has a lucky windy day. Well, wind's all very well, and you notice that people are measuring times to 100th of a second. They worry about records plus or minus 100th of a second. But how accurately is the wind actually being measured? When you look into this, you find that this is the great weak point of modern track and field athletics technology. This limit that we've got of 2 meters per second was something that was adopted back in 1936 by the International Athletics Federation. And it's somewhat arbitrary to us today, but it had a rationale at the time. It derived from the fact that they were timing by hand at that time, and the greatest accuracy was 0.1 of a second. So they wanted to rule out the possibility that the wind assistance would create a record with a change of plus or minus 0.1 of a second. So today, now that you're keeping records to 0.01 of a second, you really need to know the wind speed as accurately as 0.2 of a second, at least. Otherwise, somebody who you think is wind assisted may not be, and may have set a record. Well, how is the wind measured in athletics? Well, rather crudely, I think is the answer. Something that looks a bit like this is planted in the ground halfway down the straight, 50-meter mark. It's very precise instructions. It's at the 50-meter point, and it's at 1.22 meters above the ground, so that it's sort of going to catch the wind where the athlete's torso is hitting, and it's 2 meters or less away from the side of the track. Well, if you've walked down by the start of a track with a big stand, you know that there's huge variation in the wind caused by the presence of the stand and the change in the seating levels around the edge of the track. And the wind also varies along the straight. It can be rather different at one point to another. So in practice, the accuracy of a wind gauge over the period of the race is really somewhere between 0.2 and about half a meter per second. It's not really consistently as good as this. And where you put the wind gauge also produces a different result. So here's some research that was done on this by Linthorn at Brunel University. This is a plot of the official wind speed measured by that wind recorder at the 50-meter point, compared with wind readings that he obtains by putting another recorder at the 30-meter point. And he does other experiments with it at the 70-meter point. So if the wind speed was consistent all the way along the race, all these data points would lie along this line, and you would have the same wind speed at the 2 points. Well, I think even if you're not a statistician, you can see that this ain't really the case, that there is very significant variation in the measurement of the wind from wind gauges in the two locations. If you're running a 200-meter race, of course, there's an entirely different problem to worry about with the bend and the straight conditions. Well, the last a sort of running thing like this about wind and records. It's a notorious problem. We've talked about the men's world record. Alas, the women's world record is fraught with problems. It stood for a very long time. It was set by Florence Griffith Joyner. It's known as FloJo. Died of a heart attack a few years ago. And her world record that no one has really ever got anywhere near, either before or since, supposedly 10.49 seconds. Well, this was set in 1988 at the American Olympic Trials. FloJo went on to win the Olympic Games, 100 metres and the 200 metres, set the world record in 200 metres as well. At those trials, in the semi-final stage, with a wind reading supposedly of 0, she ran this 10.49, which broke the world record by 0.27 of a second. At the same time, we know that just parallel in the jump runways, the long jump, triple jump, jumps were being measured as having 4 metres per second following winds. And the next semi-final that came up after hers, a couple of minutes later, had a 5 metre per second following wind. So I think the charitable conclusion is that there was a failure of the wind gauge. Okay, this was a wind-assisted performance. The other athletes in the same race also experienced dramatic improvements over their performances in the first round and in the final. In the final, there was a 0.9 metre per second tailwind. Flojo won with a winning time of 10.61. And so that probably is what the real women's world sprint record should be. It's still the next best performance of all time. The other place that's become rather topical because of wind assistance and hindrance is the new velodrome at the Olympic site in East London. And you've probably read some of the press reports. Here's a picture of the inside. I was trying to get more information about the geometry and construction of this cycling track, but I was told by the designers that it was a commercial secret, and they were not going to tell me. Well, one of the things that we do know is that there is going to be a heating of the air at track level in the velodrome. So if you've got tickets and you're sitting near the front, you may not want to take too much extra clothing. Or you could just give your tickets to me. So why would they be doing this? Well, we know the answer from the formulae we've been looking at. Remember what the drag force is when you move at speed v through still air. It's proportional to the speed squared, but it's proportional to the density of air. Now, one thing everybody knows about density of air is that hot air rises, okay? So, because it has a lower density than cold air. So, by heating the air down at track level, you will lower its density, you will decrease the drag force on the cyclists, and they will go faster. They will have a greater chance of setting records. So this is the same for everybody. It's not unfair in any way, but there may be other problems with it. So here's a little plot, taken from a sort of physics book. Here's the density of air against the temperature in sort of around the relevant area of temperature. So you see what the magnitude is. You're playing around with the second decimal place in the density, sort of 7/100ths there over this significant range. And what does that mean? Well, the drag force, okay, you see looking like that, it's worth about 1.5 seconds to Bradley Wiggins over the 4-kilometre pursuit, which is sort of the equivalent of the mile, really, in time for the cyclists. So this is quite significant when you're moving at that speed. So this is a way to try to sort of cheat the record books. And so you might argue that just as in athletics, when you have a wind-assisted performance or an altitude-assisted performance, those records are sort of starred. They're marked as being special in that way. That any records that you set in London should be starred in this way as being sort of wind-assisted in this way. So here's how the drag changes over 3 temperature ranges as you move at different speeds. And you can see because of this speed squared factor, the effects get much more pronounced in the shorter events where you go faster rather than in the longer events where there's a cumulative effect. Well, the last tip for Mr. Bolt is to run high. That is, go to high altitude. Altitude was something that came into the world of athletics in 1968 when the International Olympic Committee, in their wisdom, decided it would be a good idea to hold the Olympic Games in Mexico City at a height of 2,250 meters above sea level. This produced a storm of controversy, and lots of leading athletes just didn't go because they felt it was so biased against people who were not born at altitude. So what's going on there, of course, is that as you go to high altitude, the density of air is being diminished. And so that resistive force, the drag force from the air, is being reduced. Rho air is going down, not through the temperature necessarily this time, but through the air pressure being lower. Well, each 1,000 meters that you go up from sea level will reduce the air density by an amount that's worth about 0.03 of a second for a 100-meter sprinter compared with sea level. So in Mexico City, you're looking at a 0.07 of a second advantage over sea level performance. The Mexico City Olympics were sort of revolutionary and innovative in many ways, not just through being at altitude. They were the first where there was fully electronic timing, the first where there was drug testing, the first where there was gender testing, and also the first where there was artificial track surface. So at the Tokyo Olympic Games, they still use a cinder surface. So here they used rubberized, so-called tartan surface. Much more reliable, much faster, dramatically better for people like triple jumpers. So there were a huge number of world records in Mexico City. And on average, the track sprint records were improved by about 1.7%. Really much bigger than you would expect just from the altitude alone. But the nice track surface and so forth must also therefore have been a contributory effect. To get a sort of picture of that, if there'd been a 2 meter per second following wind, you remember it helps you by 0.2 of a second. So going up to this altitude helps you by 0.07. So it's not as much as having a following wind, but it's still significant. Of course, if you're in the distance events, for other reasons, the effects of the altitude were disastrous if you were not climatized and used to it. And times were far, far slower in those events. So our final recommendations, as it were, for Mr. Bolt is that what he can look to hope for is by improving his reaction time, by being a little more alert and responsive and concentrating better and doing the type of psychological training that sportsmen do to try to respond more quickly, he can look to improving maybe by 0.03. He could also try to take advantage of 2 meter per second following winds, because there are certain stadia in the world that you know are always windy. And also he can try and race as high up in the air as he can in high altitude venues. So what would that mean? Well, his 9.58 second record, which so many people think is totally unapproachable, just from his reaction time improvement, he could reduce it to 9.55. If he allowed himself the maximum following wind, he goes down to 9.44. And if he goes up to Mexico City, then he's down to 9.37, all without any actual extra improvement in his sprinting ability. So you can see he's really got a lot of scope to take this record sort of a long, long way down. And he tends to run the 200 meters about twice as fast as the 100. You're looking at about 18.7. As a final comment, though, to take the wind out of his sails a little bit, at the end of the season, he's really found that he was perhaps no longer the fastest man because his training partner, Nathan Blake, ran a 200 meters in 9.26 seconds. At first, you think, well, this is a little bit slower than Bolt's world record of 19.19. But Blake had a fantastically slow reaction time, 0.2 of a second or something like that. So when you allow for that, Blake actually runs faster now than Bolt. So his running time over 200 meters faster than Bolt. So if you've got tickets for the 100 and 200 meters, let me have one. And so I hope that when you watch these races in the future, you'll have a little more insight, perhaps, know a little more, and have a better feeling for what's going on and why people worry about wind speeds and reactions and what the effect actually is on record performances. Thank you.
regarding the effect of altitude, especially for longer races, does not the much lower oxygen concentration have a much bigger and adverse effect?
Oh, yes. I mean, 100-metre sprinters don't breathe at all, typically. They might take one breath in their race. But once you get beyond 400 metres, you're then encountering events where there's a build-up of oxygen debt, as it were, and waste products in the system. And your performance is determined by the ability of your body to deal with that and to run in this oxygen debt state. So up to 400 metres, the body doesn't really care whether it's running at sea level or on top of a mountain. But once you get to beyond 800 metres, really, I mean, maybe 800 metres nowadays, they don't worry too much, but certainly 1,500 metres and beyond, there's a significant difference in running at sea level and running at altitude, because there's less oxygen, as it were, per breath entering your system, but also the oxygen is a different pressure, and the body is not absorbing the oxygen as efficiently at that pressure as it would if you were acclimatized. Okay, so if you spend time at altitude, you adapt temporarily, and you can absorb oxygen efficiently at lower pressure. So that's why people go and do altitude training. They can gain some acclimatization to that. But if you just go to Mexico City as a tourist and you find the lift's broken at your hotel and you have to carry your luggage up to floor 26 or something, you will notice the effect of altitude.
Hello? I see.
I think there's one at the back.
Yes. With respect to Mexico City, how do we explain Bob Beeman's long jump in view of which far exceeded any predicted increment, such of the sorts that you've cited? It far transcended any kind of external input on his performance.
Yeah, that was a very special performance that can't be explained just by altitude. I once wrote an article about this from a sort of mechanical point of view. What was achieved by him there was, I mean, contrary to what you might think, when you fire a projectile, you get the maximum range by launching it 45 degrees, if there's no air. But long jumpers don't take off with anywhere near that angle. You know, they're down closer to 10 degrees or something like that, because of the speed with which they want to come in. They're not strong enough to take off with a greater angle than that. And what Beeman did, in effect, was to take off with his usual takeoff speed, but with a significantly bigger angle than had been achieved before. But it was only a couple of degrees or so bigger, but it makes a huge difference in the range. He never got close to that performance himself again, although it was eventually beaten, of course, by Powell and also by Lewis in the same competition. One more. Yeah.
Since I assume the power factor is what you can apply to the ground, and in 1968 they were using the new model brush spikes rather than what now legal. Do you think that can make a difference?
Well, the brush spikes were actually banned at the Olympic Games, before the Olympic Games in 1968. They were worn at the Olympic trials in 1968, the American Olympic trials. And the 400 metres, for example, Evans set a world record with those. Carlos set a world record in the 200 metres wearing those shoes. But they were banned, and they weren't used in the Olympic Games. So for non-experts, these were running shoes which, instead of having 4 or 6 conventional spikes, had 400 tiny little needles. And so they gave fantastic grip across the whole of the foot. Trouble was, they give rather too much grip, and they're going to damage your knees when you run round curves at high speed. So they were outlaws on sort of grounds of what would now be called health and safety. But fortunately, the records that were set with them were beaten at the Olympic Games, by the same people, in fact, who set them, the trials.
Thank you. Usain Bolt being big, if he had the tailwind, would he get more advantage than a smaller colleague?
Well, you can see that the real factor about his size is that he's really feeling much more resistance. The resistance you feel is proportional to his area. Okay, so having the tailwind just reduces the effect of the air that he's got to run through. It doesn't reverse it. So he's actually at a disadvantage by being so big in this respect. Okay, so if he could reduce his surface area significantly, okay, then he would have correspondingly less air resistance to encounter. But there's a trade-off here, and it's one of the things we'll talk about in the next lecture. If you reduce your size, you also reduce your strength. Okay, so there's always a trade-off. So you might think, oh, sprinters should be really small, okay, and have a small surface area. But if you reduce your size to have a small surface area, you also reduce the power and the strength that you can generate, which happens to scale in exactly the same way as your area, as your size squared. So he shouldn't shrink. He will lose strength at the same rate that he reduces his surface area. But for long-distance runners, it's a very slightly different equation. So if you're a very small distance runner, your surface area determines how well you can keep cool. Okay, whereas your volume determines the rate at which you generate heat. So it pays to be small if you're a very long-distance runner in a hot climate. Okay, that's the end for today.